Okay, 18.3 has to do with entropy and temperature. And the real question that we're trying to get at with section 3 has to do with the fact that we can see processes where the delta S naught of reaction is less than 0. It's negative. In fact, the example we looked at the very end of the previous section was an example of that. However, our second law of thermodynamics says that delta S for the universe is always greater than or equal to 0. And so your reaction is not the universe, and so there's going to be some sort of an offset which will make sure that the second law of thermodynamics is obeyed, even for processes where delta S of reaction is less than 0. Well, we're going to kind of explore how to calculate the delta S of the universe and the delta S of your reaction, which from now on we'll just say the delta S of your system. You may recall in 1210 there was some discussion about system versus surroundings, and you have closed systems and isolated systems and open systems. And really what we mean by the system is just the molecules themselves that are involved in a chemical reaction. If it's forming new bonds or breaking old bonds or changing phases, it's a part of the system. Everything else is a part of the surroundings, and that includes like the solvent that is the environment where a chemical reaction will take place, the vessel that your reaction is contained in, and any apparatus that you use. Like if you put a thermometer in to your reaction, then any temperature change that you observe on that thermometer is really a change in the temperature of the surroundings, because your thermometer is a part of the surroundings. If it heated up, it's the surroundings that heat it up. And anyway, just being very particular about what we define as the system will kind of help you to avoid some confusing pitfalls when we're talking about this sort of topic. So anyway, what is the delta S of the universe? That's going to equal the delta S for your system plus the delta S for your surroundings. And how you find the delta S for the system, that is your delta S of the reaction. We talked about that in the last section, so we already have this covered. You're going to look at your balanced chemical reaction, find the standard molar entropies for your products and for your reactants, and that'll give you an entropy of reaction. And if you have more or less than 1 mole, then you'll have to multiply that by the number of moles, just like for an enthalpy of reaction. To find out how much heat is actually released, you might multiply the enthalpy of reaction by the number of moles. So that's easy enough, but what about the surroundings? Okay. Now it's key here that the surroundings is actually going to be a lot simpler than everything else, because there are no chemical reactions that occur in the surroundings. Again, by definition, anything that is reacting we put into our system. And so the surroundings are not forming any new bonds or breaking any new bonds or changing phases. The substance of the surroundings is not changing. And so to find the delta S here, we're actually going to go back to that original definition of entropy. So the delta S for the surroundings is going to equal the Q for the surroundings. That is the heat divided by the temperature. And in principle, if the temperature changes, this could become an integral and we'd have to use a bunch of calculus, but we'll just look at simple cases where the thermal heat capacity of the surroundings is large enough that the temperature remains constant. Even for exothermic and endothermic processes, right, the temperature of the universe as a whole doesn't change much, and so we'll say that T is constant. Now what is the Q of the surroundings? That is equal to the negative Q of the system. Okay, if the system has lost heat, that's an exothermic process, then the surroundings are gaining that heat. It should be a positive value. And if you have an endothermic process, if the Q system is positive, then the surroundings should have a negative value there because the heat is being taken away from the surroundings. So the Q surroundings is the negative Q of the system, and that's divided by temperature. So now we have a way of calculating the enthalpy of the surroundings. And I guess we can take this one step further. That would be the negative delta H of reaction times the number of moles over T is the Q of the system. Okay, so let's look at a couple of examples here. And hopefully we can sort of validate our second law of thermodynamics. Otherwise, we'll go to thermodynamic prison. So find the delta S for the system and the surroundings and for the universe for this process. Combustion of 1 mole of methane at 298 Kelvin. And so if I have CH4 gas plus, what will it be, 2O2 gas, this will form CO2 gas plus 2 H2O gas. There we are. That is the combustion of methane. And we'll want to calculate the delta H for this reaction. And we'll want to calculate the delta S for this reaction. Those will both be standard molar values. Okay, so we would do that by looking at the table in the appendix. But since we've already covered those in previous sections, I'm going to be a bit of a cheater and just look it up. Google has actually failed us in formatting here a little bit, but it shows a enthalpy of combustion for methane of negative 890.8 kilojoules per mole, negative 890.8 kilojoules per mole. And okay, I actually went and looked up the values and calculated it because I wanted to make sure it was consistent, and sometimes thermodynamic values you find on the internet are at 0 degrees Celsius instead of 25 and things like that. So these are our values. Delta H of the reaction is negative 802.5 kilojoules per mole, and delta S of the reaction is negative 5.30 joules per mole Kelvin. So our delta S for the system, because we have 1 mole, this is going to be easy. That is equal to negative 5.30 joules per Kelvin. We'll just multiply it by the 1 mole. Delta S for the surroundings is going to be the negative delta H naught of reaction times the number of moles. This is the delta H naught of reaction, and again, it's just 1 mole, so that's easy. That's an 802.5 kilojoules per mole. I'm going to go ahead and convert that from kilojoules into joules so that it will match the units we have with the delta S. So 802,500 joules per mole times 1 mole is just 802,500 joules, and we'll divide that by 298 Kelvin. So delta S of the surroundings, let's just quickly calculate that. There we go. 802,500. Oops. 802,500 divided by 298. That's going to be 2,000, a positive 2,693. 2,693 Kelvin is the value for the delta S of the surroundings. And so delta S of the universe is just the sum of those two. Delta S universe is going to be 2,693 Kelvin plus a negative 5.3 Kelvin. We really only get a couple of sig figs on this, but I'll carry this out to the ones place just to sort of be extra cautious with not throwing away potentially significant figures. So we get 2,688, that should have been joules per Kelvin, joules per Kelvin. And we see that this is indeed greater than or equal to 0. The second law of thermodynamics has been obeyed. Let's look at one more example. Okay, so condensing 1 mole of water at 373 Kelvin, or in other words, at the boiling point. If we condense 1 mole of water at the boiling point, what's delta S of the system, of the surroundings, and of the universe? Well, we know that delta H of vaporization, the enthalpy of vaporization for water is 2,000. Oh, you know what? Let's do, I see why I did this. Let's do 1 gram. I had converted that to 1 mole because I thought it would make the question easier, but Dr. Rowley of 6 months ago, who wrote these notes, knew what he was doing, because I have a enthalpy of vaporization in terms of grams. 2,257 joules per gram. And so let's figure out what will be delta S of the system. Well, we'll need a delta S of vaporization. I guess it's back to the table for us. And I'll let you watch me do this. All right, so here we have the standard molar entropy for gas and the standard molar entropy for liquid. So we'll figure out what their difference is. That's that was 188.8 minus 70. 188.8 minus 70. And so that's the standard molar entropy of vaporization is 118.8 joules per mole Kelvin. And then I'm going to go ahead and say that if I have 118.8 joules per mole Kelvin, and let me get this out of the way for a moment. Let's turn it into a per gram basis just to make our life a little easier. And we'll say that 1 mole of water is 18.015 grams. And that'll give us joules per gram Kelvin and make everything a little bit easier. So we'll take the 118.8 divided by 18.015, and I get 6.59. 6.59 joules per gram Kelvin. Okay, so delta S of the system, if we have 1 gram and it's 6.59 joules per gram Kelvin, that's for vaporization. Condensation is the reverse of that, and so delta S of the system will be negative 6.59 joules per Kelvin. Delta S of the surroundings, if the enthalpy of vaporization is 2,257 joules per gram, condensation is going to be a negative 2,257 joules per gram. but delta S of the surroundings is the negative of the delta H of reaction, and so that negative will then be a negative of the negative, makes it a positive again. 2,257 joules. We have just the 1 gram. And we'll divide that by our boiling point of 373 Kelvin. Hopefully you follow that. Condensation has a negative delta H. Delta S of surroundings is the negative of the delta H. And so those two negatives cancel out. So let's figure out what delta S of the surroundings is. We've got 2257 divided by 373, and it looks like that's a positive 6.05 joules per Kelvin. Okay, and I wonder if my enthalpy of vaporization value was off a little bit or was subject to some rounding, because what we should have found here is that the delta S of the universe, I'll just say it is approximately 0. And you'll see we've got about 1/2 of a joule per Kelvin left over. I'm going to chalk that up to rounding approximations. But for this process, this is one of those where the second law is obeyed by the change in entropy of the universe being equal to 0. Remember, it must be equal to or greater than 0. Well, condensation of water at the boiling point ought to give you 0. We'll talk a little bit more about why that is and sort of what delta S of the universe equal to 0 really means in the next section. But for now, that's just meant to be our interesting result, and I apologize that my rounding has made that not quite work out, but it was supposed to be equal to 0.